Right, so welcome to this lesson on seeing things, and also pretty much it's going to be covering the idea of how we correct vision if it's wrong. Okay, so standard stuff from the previous lesson. Light rays come in from quite a distant object in this case. They get refracted at the cornea. In fact, most refraction takes place here, and then the lens does the fine focusing and gets it to focus exactly on this back part of the eye, the retina. Okay. Right, so looking at seeing things from different distances. In the first example, we've got parallel rays of light. That means the object is far away. So this one might be coming from the bottom of the tree. This one is coming from the top. But the tree actually forms a very small part of the overall image because it's far away. Okay, there'd be other stuff going on. In this case, the lens has to be long and thin. That's because you don't need to refract this light very much in order to focus it here on the retina. So it hits the cornea. It would actually bend at the cornea at this point, and then it hits the lens, and then it refracts and it focuses on the retina. Okay, and that's all because of these ciliary muscles down here affecting the shape of the lens. So when the objects are distant, the ciliary muscles relax, okay, which pulls the suspensory ligaments tight, so these things become longer and tighter, okay, and the lens pulls thin, it pulls long and thin, so it doesn't bend as much. The fatter a lens is, the more curved it is, the more it will refract light. In the next example, I'm not quite sure I like how the rays are drawn, but imagine it's coming from, say, the top and bottom of a book. Now, that book, because it's close up, actually forms a large part of your field of vision. So we're getting rays coming from near the top of your field of vision, near your bottom, so they come outwards. Now, in this case, because they'd continue to travel something like that and be very far apart, you need to refract it a lot, okay, to bring it again in focus on the retina. So in that case, again, it refracts at the cornea, and then the fat lens refracts it more and it focuses. Now that's because the ciliary muscles have contracted, okay, and they've come up a bit, alright, so the suspensory ligaments go slack, there. Okay, and the lens becomes shorter and fatter. By the way, naturally, your lens is used to looking at long distances, okay? It actually requires effort for the muscles to contract and pull the lens short and fat, and that's why over time you begin, your vision begins to deteriorate. Okay, so we'll look at short-sightedness first. This is when the eye cannot focus on distant objects, okay? And what we call the uncorrected image, so this is if you're looking at it without glasses on, forms in front of the retina. It's one of two things. The eyeball is too long, it's become slightly stretched, or the lens is too powerful. Okay, and the eye can only focus on nearby objects, hence its short sight. Okay, so you can't see faraway objects. And this is how it happens. So parallel rays of light come in, okay, from a distant object, okay, because the eyeballs may be a bit longer than it needs to be, you actually end up getting them focused in front of the retina. So your image would be formed here, and what would actually happen, these rays would continue, and instead of getting a sharp image here, you'd get a much blurrier image here, which is why distant objects look blurry. Okay, so what you do is you add a diverging lens. What you've got to do is spread these rays of light out a bit first, so then when it comes in, it focuses on your retina here. So this is what happens, okay? This one comes in at 90 degrees so it doesn't get refracted. That's that one. These ones, this top and bottom rear, get refracted outwards. Then when they hit the lens, okay, they get refracted and they actually hit the retina. Okay, so you get the corrected image. So people who are short-sighted, they can't see objects far away. They'd be fine with an object that's close up, because remember, the rays of light are coming in something like this, where they already need to be bent a lot. Okay, long-sightedness, alright, the eye cannot focus on nearby objects. The image forms behind the retina, and the eye lens cannot thicken enough to focus the image on the retina. Okay, so long sight, we've got a nearby object, so we've got these rays of light coming and spreading out, so it's covering a large part of the field of view, and they hit the lens isn't thick enough, or the eyeball's too short, one of those, and we get our image formed here. Okay, so again, it would be blurry, along the retina here. So what we do is we add a converging lens, and that converging lens will bend light more than it is currently bent, bend light in more. Okay, so it bends light, okay, here and here, then light's bent again at the lens, and you end up getting your perfect image formed on your cornea, on your retina. So one of the things we've got to know about is lens power, okay, and the power of a lens measured in something called diopters is 1 divided by the focal length in meters, and that's a key thing. In the exam they will try and catch you out by putting values in centimeters. Okay, so diopter, so it's power of lens, P, equals 1 divided by the focal length. Okay, so we got this. So what is the power of a conversion lens of focal length 0.05 meters? So that's already in meters, okay, and that would be 20. Okay, so it'd be 20 diopters. And what we get is a positive value for the power of a convergent lens, okay, and a negative value for a divergent lens. So if you've ever been to the opticians and you've been given one of those cards that might say something like plus 0.5, plus 0.25, and it might say right eye, left eye, okay, that would be the type of lens you would need to correct your eye. Okay, so I have about, I think I'm about plus 1.5. okay, so I have a converging lens because I'm long-sighted with a power of plus 1.5 diopters, okay, and I think my left eye is about plus 1.25. so again, converging lens, slightly less strong. Okay, so this one would be less fat. Okay, this one would be fatter. You get a negative value for a divergent lens. So for those people who are short-sighted, you'll be given a divergent lens, and your values will be negative. Okay, so it might be minus 1.75. Okay, in which case you'll have a divergent lens, which will correct your vision. The final thing we need to be able to do is compare the eye with the camera. Okay, so very simply, you just need to be able to say how they're similar and how they're different. Okay, usually maybe 2 or 3 points. So the eye has a variable focus converging lens. Okay, so when we say variable focus, it means the lens itself can change shape and change the focus. The camera doesn't have that. It's got a fixed focus converging lens. Okay. When we're focusing, the eye uses ciliary muscles to alter the thickness. The camera moves the lens, so it might start here and then go and then move the lens a bit further back. The image formed, okay, both are real. They've got to be projected on the screen. In our case, it's the retina. In a camera case, it's the back of the camera, the screen and back of the camera. They're inverted, okay. and they are diminished, which makes sense because the back of our eye and the back of a camera are much smaller than what we're looking at. Image detection is by light sensitive cells on the retina in our eye, and it's by photographic film or sensors in a digital camera, more usually sensors now. Brightness control, we've got the iris, okay, which controls the width of the pupil. So if you're in low light, you'll have a very small pupil, okay. If you're in low light, you'll have a very big pupil taking lots of light. If you're in high light, you'll have a very small pupil. And then we've got the brightness control in the cameras, something called the adjustment of the aperture. So you'll see something that looks like this on a camera, okay, and you can change the size of this, or you can change how long the camera, how long the image is taken for. Okay, final thing, alright, so when you're making lenses, you've got to make sure you get the right shape to extend the exact focal length, okay? And the focal length depends on the refractive index of the lens material, so maybe like glass and diamond would be different, and the curvature. The larger the refractive index, or the greater the curvature, yeah, the greater the power of the lens, okay? So what you could maybe do, if you've got a very high prescription for glasses, which gives you big jam jar glasses, you could maybe make it out of a material that's got a higher refractive index, so your glasses wouldn't have to be as thick.